Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to talk about complex ion equilibria, and I'm going to go through an example of a problem dealing with the formation of complex ions. So here in this problem we're given 200 milliliters of a 1.5 times 10 negative 4 molar solution of calcium nitrate. And we're going to mix that with 250 milliliters of a 0.20 molar ammonium solution. So after we mix them together and after we reach equilibrium, they're asking us what the remaining concentration of copper 2 ion is. And so the first thing we need to do is we need to find the concentrations resulting after we mix, because the concentrations are not going to stay the same because the volumes are being added, so we need to figure out what that is. So, so what we need to do is find the moles of each one. And so here, what we're going to have is we'll have 200.0 milliliters of the copper 2 nitrate. We're going to convert that to liters. So 1,000 milliliters of the copper 2 nitrate. 1 liter. We'll have 1 liter of the copper 2 nitrate on top. Okay, so milliliters cancels out, and now we can use the molarity, a given molarity, to find the number of moles. So this is going to be, since we have liters on the top, we want liters on the bottom. So we're going to have 1.5 times 10 to the negative 3 moles of the copper 2 nitrate over 1 liter of the copper 2 nitrate solution. So liters are going to cancel out. And that's going to give us, if we calculate that, that's going to give us that's going to give us 3 times 10 to the negative 4. So this is going to give us 3 point. Let's look at our sig figs. So this will be 3.0 times 10 to the negative 4 moles of the copper nitrate. And then we'll have to do the same thing with the ammonia. So we have 250.0 milliliters of ammonia. Convert that to liters of ammonia. So milliliters on the bottom, 1 liter of ammonia on top. The milliliters are going to cancel out. And then we're going to use the molarity they gave us. So that's going to be 0.20 moles of NH3 over 1 liter of NH3 solution. So liters cancels out. And so we can calculate the number of moles. And that's going to be 5 times 10 to the negative 2. So we got 5 times 10 to the negative 2 moles of NH3. And then now all we need to do is divide those moles by the new volume. 200 plus 250 gives us 450 milliliters, or 0.45 liters. So if we take 3.0 times 10 to the negative 4 moles of the copper 2 nitrate, divide that by 0.450 liters. And then we'll do the same thing. Give 5. So this should be 5.0. So 5.0 times 10 to the negative 2 moles of ammonia over 0.54 liters. And so if we calculate those, we get for the copper concentration, we're going to get 6.7 times 10 to the negative 4. Let me check that again. 6.7 times 10 to the negative 4 molar. And for the ammonium concentration, it would be 0.11 molar. So this is 0.11 molar. Okay, so these are the concentrations that we need after we've mixed our two solutions together. So now we mix them together. These are the new concentrations. These are the starting concentrations before anything has happened. Okay, so now what we need to do is we need to do our ice table so we can figure out what the equilibrium concentrations are going to be. So what we need to do is I'll erase this. Just give me a minute. Okay, so the next thing we need to do is we need to write down the equation for our ion complex. So here we're going to have copper 2 plus ion aqueous plus our ammonium ion. So it's going to be NH3 aqueous. And then we're going to form that complex, which is copper with 4 ammonias. So it's going to be Cu NH3 4 with, I believe, a 2 plus. Yeah, 2 plus aqueous. And so what we need to do now is do a ice table. We're going to do an ice table here. And so what we're going to start with is the initial concentrations. So the initial concentration of copper and ammonium and our complex here. So this is where this is going to come in. So the copper concentration is the same as the overall concentration of the compound, since it's a 1-to-1 ratio. So we were starting with 6.7 times 10 to the negative 4 molar, or just negative 4. So that's the concentration that we're starting with. Ammonia, we're starting with 0.11. And then to begin with, this is going to be 0. We haven't formed any complex yet. And now we're looking at the change. Now, given that the, where is it? Do I have it written down? No, the KF value. Let's look up the KF value. Okay. So the KF value is 1.7 times 10 to the 13th. So the KF value, the constant of formation, so is equal to 1.7 times 10 to the 13. Okay, so also given that this formation constant is so huge, and in addition to that, the amount of ammonium, the concentration of ammonium that they're giving us here, So the concentration of ammonium is much greater than the concentration of the calcium. That we can assume that most of this is going to go into formation of the complex. So it's pretty much going to be driven this direction, so that we can assume that hardly anything is going to be left. So we're going to lose pretty much approximately 6.7 times 10 to the negative 4. And the same with here. So we're going to lose this, and we're going to gain the same amount here. So this is going to be plus 6.7 times 10 to the negative 4. Okay. And also I should balance this equation. So since we have copper, we have four ammonias. So here we're going to lose 4 times this amount. So 4 times whatever this, because it's a 1-to-4 ratio. So because if we're going to lose all this, then we're going to lose 4 times that amount, 6.7 times 10 to the negative 4. And it's a 1-to-1 here, so that means whatever we lose here, we're going to gain the same amount here. Okay, so now what we need to do is we're going to figure out our equilibrium. And what's going to be different about this ice table is normally we use X to write our change, but here we're going to use X as the amount of our copper that's going to be left over. So we're going to use X here, and then here we're just going to do the 4 times 6.7, and that's going to be, so 0.11, right? So basically this is so small that this minus this, these two, is basically going to be 0.11. And then here, this is going to be plus 6.7 times 10 to the negative 4. Okay, so now all we need to do is get our equation, so I can erase this. And so now we're going to set up our Kf expression, and this is the equilibrium of formation, so the constant of equilibrium of formation. So this is the equilibrium expression. So it's going to be this, the concentration of Cu NH3 4 2 plus concentration over the concentrations of these two. So Cu2 plus times NH3 concentration. So now we can put in the values here. So the value here is going to be 6.7 times 10 to the negative 4 over, and then the concentrations is going to be X times whatever the concentration there is. That's 0.11, 0.11. And again, Kf is equal to, right here, 1.7 times 10 to the 13. And so now all we need to do is solve for X. And when you solve for X, you get 2.7. So X is equal to 2.7 times 10 to the negative 13. And let me double check. And so we can see here that X is going to be the amount of copper 2 left over. We can see that this is much, much smaller than the 6.7 times 10 to the 4 concentration that we started with, right? So we could say this is a valid approximation. So this is the molarity of the copper left over. I hope you enjoyed this video. I hope it was helpful. If you like my videos, like, share, subscribe, hit the notification bell, and leave a comment in the comment section.